Let's discuss a question from fluid mechanics. A pressurized tank of water is given where we have 3 meters height of water, and above that we have air with absolute pressure of 300 kPa that is given here. And now the tank, okay, that is given, and the atmosphere pressure is given. The initial discharge rate of water is asked. That means when I just open this valve, what is the discharge rate with which the water will be coming. So in this problem, discharge rate is something that is related to the velocity. So and I can see basically two levels. One is the level of I take 2 points. First is the water top, and the second level, level is the datum basically for my potential energy calculation, and the second level is the level at which the water is coming out. So these two levels, and I apply the Bernoulli equation, because always when you're dealing with pressures and velocity, the first thing in mind that should come is your Bernoulli equation, because that contains the pressure term as well as the velocity term. Okay, so Bernoulli equation, where I have P1 by rho g. Before fixing the Bernoulli, before writing the Bernoulli equation, you have to fix this datum as well as the point number 1 and point number 2, okay, because you are applying at 2 points. And datum is because you need to calculate this potential head. Z1 and Z2 are the heights of those reference points 1 and 2 from the datum. So that's why these three things are required. And now I write down these equations. Okay, so now coming to the fact here, let me write down here. P1 is the absolute, so my pressure will be all absolute, so 300 kPa. Okay, I have that. Rho is water density, which is 1000 kg per meter cube. That is something which you should know. Okay, most of the time it may not be given in the problem like here. Whereas now velocity V1, well, compared to this outlet, this is something where the velocity will be very low compared to the velocity at the outlet 2. One will be very small. So V1 is something, because of the large cross section, V1 can be assumed to be 0 compared to V2. Okay, and the Z1 is the height from this datum, which is 3 meters. Now the other data, P2, is basically the atmosphere pressure that is acting at this point. The moment it comes out, the pressure there is the atmosphere pressure, which is 100 kPa, and velocity V2 is something which we need to know, right? Once I get V2, I can multiply with that area, and that is the AV2 is the volume discharge, the initial discharge. And Z2 is 0 because my datum as well as the level 2 are at the same level. So let me substitute. P1 is 300 kPa, kPa is kilopascal, so 10 power 3 by density is 10 power 3, and G is 9.81, plus velocity V1 is 0 and Z1 is 3, P2 is 100, atmosphere pressure into 10 power. So this problem is a straight application of Bernoulli principle. Plus V2 is something which I need to find out, that is the only unknown in this equation, right? And Z2 is 0. So if I calculate this, if I calculate from this V2, I get as 21.42. So you have to use your calculator. 21.42 meters per second. And what is this? So this is the initial velocity with which the water will be coming. Remember that as time progresses, so the level will decrease. Obviously the level will decrease, and that's why the Z1 will not be 3, Z1 will be something less, and therefore the V2 also will be less, because V2 is again directly related to square root of Z from this equation. So that is the thing. So but what we asked is the initial discharge. So initial discharge is basically just at that point when the valve is open. So initial discharge is Q into initial velocity which is V2. And as it is circular, so area of cross section is pi by 4 d square or pi r square, and diameter is given, so we use pi by 4 d square. So pi by 4, diameter is 10 centimeters, so it is 0.1 meter into 21.42. so this comes out to be 0.168, okay, meter cube per second. That is what is asked, 0.168 meter cube per second. So that is the answer. So this is a straight application of Bernoulli's equation. Thank you.